I'm Anil Kumar. This video is for my student Faiza, who wants to review all about logarithmic functions in half an hour. So I've taken few important examples to cover the topic. In this video, we'll talk about exponential functions and logarithmic functions and how they are related. So we'll take up an example with f of x equals to half to the power of x and its inverse, which is a logarithmic function, and discuss all these characteristics which are written on the left side. And then we'll take up simple examples of how to evaluate each of the given logarithmic expressions. We'll go further with some difficult examples on evaluating logarithmic expressions, and then we will see how to rewrite logarithmic expressions as exponential functions, and then we'll solve exponential equations given here. Now these equations can be written in with same base, and they are kind of easier to solve than what comes next. Then we'll take up equations which have different base, and we may have to use logarithms to solve these equations, right? And then we'll have simple examples on expressing logarithms, applying the rules as single logarithms. And then we'll solve few equations relating logarithms. A reminder to you, some solutions could be extraneous roots, right? You can actually go back, pause video, copy questions, do them yourself, and then look into my videos for suggestions. So let's really begin by understanding exponential and logarithmic functions first, and then we'll get to all what I shared with you. To understand logarithmic functions, we should actually review exponential functions. Once we understand exponential functions, it forms a good foundation for us to move forward with logarithmic functions. So here is a quick review on exponential functions. Let me write y equals to b to the power of x, where b is the base and x is the exponent, right? Now on the base, we have restrictions that b should be greater than 0 and b is not equal to 1. The reason is, if it is negative, the points on the graph will go up and down, right? If b is negative, right? Negative to the power of even is positive, negative to the power of odd is negative, so we'll not have a continuous graph. And if b equals to 1, we'll have a horizontal line. 1 to the power of anything is just 1. Perfect. So we don't have exponential growth or exponential decay. So I hope this is very clear. So these are restrictions on the base. There are no restrictions on x. X belongs to real numbers. So there are no restrictions on the independent variable x in this particular case. Correct? So we'll look into two scenarios always. Let's say one is when b is greater than 0 but is less than 1. And the other one will be when b is greater than 1. Correct? So based on these scenarios, we have two types of graphs when we work on exponential functions. So let me sketch these here. One, when it is increasing, b is greater than 1, we call it exponential growth, which will be kind of like this. And if b is less than 1, then we have exponential decay, so where it is going to come like this. Correct? So these are two graphs. So when b is between 0 and 1, we have a graph which is kind of a decay. And when b is greater than 1, we have growth. Correct? So let me write here. When b is between 0 and 1, you see always it is decreasing, right? So it is always decreasing. However, if b is greater than 1, the base is greater than 1, in that case, it is always increasing. Correct? Now, you find that both of them have common y-intercept, and the reason is that anything to the power of 0 is 1, right? And therefore, this point which is 0, 1 is y-intercept. Another feature which is very conspicuous here is horizontal asymptote. So we have a horizontal asymptote. And what is the equation of this asymptote? X-axis, right? X-axis. Whose equation is? Y equals to 0, right? Y equals to 0. And as far as domain and range is concerned, let me write domain. So domain for this function is, as we have seen earlier, no restriction on x. X belongs to real numbers. And the range is y is always greater than 0, right? So y belongs to real numbers. However, y is always greater than 0. So that becomes domain and range for the given function, correct? Now let's move forward and try to understand how logarithmic graph should look like and what are its key features, correct? Now, as you understand, logarithmic functions are inverse of exponential functions. Correct? So if you have to sketch inverse of exponential function, how will you do it? So let me take the example for exponential growth, sketch it here for you. So we are considering b, the base is greater than 1, and we want to sketch inverse of this function. So standard technique is swap x and y, which could also be done by reflecting the graph on the line y equals to x, correct? So if I reflect this graph on y equals to x, the horizontal asymptote becomes the vertical asymptote, right? The y-intercept becomes the x-intercept. So what I get here is a graph like this. So this graph is for log to the base b of x. Do you see that? So logarithmic function and exponential functions are very much related. They are inverse of one another. So basically we can write every exponential function as a logarithmic function. Do you appreciate that part? Perfect. Now, based on this, I'd like you to, I've done the diagram for log to the bx. Now, if I have log to the base bx, and if b is less than 1, however, it has to be greater than 0, in that case, I'd like you to sketch the graph of log bx. Okay, so that is an exercise. So that's to do. Sketch graph. Okay, so let this be your exercise. I've already done for b greater than 1. Is that okay? So I've done for log to the base b of x. Now let's talk about these characteristics. Since we know it is an inverse function, so wherever we have decreasing, it remains decreasing, increasing is increasing. So what we really see here is that if b is between 0 and 1, then logarithmic function should be decreasing, right? Since exponential function is decreasing, both are same thing, just the inverse of one another, right? Don't confuse with reciprocal. When b is greater than 1, as you can see, it is always increasing. So logarithmic function is always increasing if b is greater than 1, just as exponential function is, and it is always decreasing if b is between 0 and 1, just as the exponential function is. Very important to understand. Okay. Now, what happens to all these characteristics? The y-intercept, which was 0, 1, becomes 1, 0 because you have to swap for an inverse. So that means now x-intercept is 1, 0. Okay. We don't have horizontal asymptote, we have vertical asymptote. So there are no y-intercepts, as you can see, and x equals to 0 is the equation of vertical asymptote. Instead of y equals to 0, which was horizontal asymptote in exponential function. What happens to domain and range? As you can see, domain range flips. Earlier domain was all real numbers. Now range becomes all real numbers. Earlier range was y greater than 0, and now domain becomes x greater than 0. Perfect. So that is how they are very much related. Now with that, let's move forward and try to understand more characteristics in details for specific example, which I left here as an exercise for you, right? So pause the video, do your exercise, and then move forward and check your result. Now let's move forward with our list of things which we have to do in this video. I've left this as an exercise. Now I'll solve it for you, and you could do similar examples from your textbook. So in this particular part of the video, we will understand characteristics of logarithmic function and exponential function. We are taking base as half, right? So let me sketch both the functions here, and then we'll discuss their characteristics. When the base is half, that means b is between 0 and 1, we know exponential functions will have exponential decay, right? It's kind of like this. And if you want to sketch from the graph inverse of the function, you could always reflect it on the line y equals to x and get the result. So that becomes invariant point for you, right? So all these x and y values flip. So the y-intercept becomes the x-intercept for you, right? The horizontal asymptote, which is right here, becomes a vertical asymptote, correct? And this is invariant point for you. So all the points will flip, and the graph, which you will see, will be kind of like this, going through the invariant point and coming down like this. Is it okay? So if you take some values and draw it on a graph paper, you will get a very good result, right? This more or less like this. So what we have here is the graph of the function log. Let me write down here. So this function is log to the base half of x, correct? And now from the graph, it becomes easier to write the characteristics. So we should be in a position to fill up this form very easily, correct? As far as the exponential function goes, you know, domain is x belongs to real numbers. Range is y also belongs to real numbers. However, y is greater than 0. X-intercept, we are talking about the function half to the power of x. So x-intercept is none. Y-intercept is at y equals to 1. Increasing interval, it is never increasing, right? Decreasing interval, it is from minus infinity to plus infinity. It is always decreasing. Let me push the page a bit. Asymptote, we have horizontal asymptote, which is y equals to 0. Positive interval, it is positive always from negative to positive interval, and negative interval none, right? So these are the characteristics of the exponential function. To write down the characteristics of logarithmic function, we know that domain is restricted and x belongs to real numbers. However, x has to be greater than 0, as you can see from here. Range, there is no restriction. Y belongs to real numbers. X-intercepts, yes, we do have x-intercept at x equals to 1. Y-intercept is none, since we see that as a vertical asymptote. Increasing, never. Okay, it is always decreasing. So it is decreasing in this interval of its domain, which is from 0 to infinity. Asymptotes, we have one asymptote, and which is x equals to 0, a vertical asymptote, correct? In this case, it was a horizontal asymptote. Positive interval, now positive interval, this point is at x equals to 1. So we do have a positive interval. So let me write here, f of x is greater than 0 at from 0 to 1. Is it okay? That is very interesting. Negative interval means f of x is less than 0 it is less than 0 after 1, right? So from 1 to infinity, for a decaying kind of a function, exponential function, that is what you get for negative interval. Perfect. So I hope these characteristics are very easy to understand once you make a sketch. So I like you to take few other functions and then write down their domain range, x-intercept, y-intercept, increasing, decreasing intervals, asymptotes, and where the functions are positive or negative. Okay, so let's move on to the next page now. Now let us try to understand how to evaluate logarithmic functions. The idea here is to write the value of x in terms of its base, and then it is very, very easy to evaluate any logarithmic function, right? So the property which we are going to use here is that if we have log to the base b of b to the power of n, then the answer is n. That is the value. So log to the base b of b is always 1, correct? So we get this as the result, and that is the property which will be utilized to evaluate logarithms in this particular exercise, and you can always do it, right? If you want to write it in exponential form, look here. If you want to write it in exponential form, this equation b to the power of n goes there, then we have b to the power of n equals to b to the power of n. It works perfect. So that is the key. So let's begin. So if I have log to the base 2 of 16, then we basically need to write 16 as 2 to the power of what? In this case, 2 to the power of 4 is 16, and therefore this is equal to 4. You get an idea. Now here we have log to the base 2 of 0. Now here does not exist is the answer. Can you tell me why? Because the domain is restricted, right? So the domain x has to be greater than 0. Otherwise, you cannot find log of a function. Do you see that? Now, if you go back to exponential functions, anything to the power of what will give you 0? Nothing, correct? That is why. That is the answer. If I have log to the power base 7, 7 to the power of 5, straight away, using this rule itself, we could write answer as 5. Is that clear to you? So that is the strategy which you need to adopt to answer these questions. So let's do them quickly. How can I write 1 over 9 as power of 3? Well, I could write this as log to the base 3, 3 to the power of minus 2, correct? That minus 2 brings 1 over 9. So the answer is minus 2 here. Log 7 of 1, right? That means anything to the power of 0 is anything to the power of 0 is 1. So we could write this as log 7 of 7 to the power of 0. Perfect. Anything to the power of 0 is 1, and so we get that result, right? The last one here is log to the base square root of 2. Now how can I write 4 as square root 2 to the power of something? If I square it, I get 2, and square root of 2 is 4. So fourth power will give me the result. So this is 4. Perfect. I'll leave this for you to work. Well, when we say log and we don't write any base, it really means the base is 10. So treat this base as 10. Perfect. 10 to the power of 1 is 10. So this is 1. Is that okay? And here we have to write 8 as half to the power of something, which is similar to this example. I'm going to leave this for you. And this is what? 10 to the power of minus 3, right? So if I do 1, 2, 3, it works. So we could write this as log base is 10, 10 to the power of minus 3. So that should be equal to minus 3. Perfect. So with that, let's move forward. Now you know how to evaluate logarithms. Now here are a few difficult questions for you. So I've just taken 2 of them. So the idea is to write all this in terms of 5. Perfect. So let's do it. We have log to the base of 5. 125 is 5 cubed, right? So let's see how to write this. So let me go for it as layers. So this is 12 outside. Inside we have to the power of 1 over 4. Let me write 1 over 4 here. 1 over 25 means 1 over 5 cube, right? 5 times 5 times 5 is 125, correct? Now, I could actually now write this as applying the exponential rules. Since this is in the denominator, I could write this as 5 to the power of minus 3, is it okay? To the power of 12 times 1 over 4. So I can write this as 12 over 4, right? Okay. And this could be written as log to the base 5 of 5 to the power of. Now if you do your maths, 12 divided by 4 is 3, and 3 times minus 3 is 3 times 3 is 9, right? So 3 times 3 is 9, so you get minus 9, perfect. And therefore, the answer is minus 9, correct? Okay, let's do this one now. So we'll follow exactly similar steps. We could write this as log to the base 8. And how do I write 16 as 8? Well, we know 2 cube is 8. Is that okay? 2 cube is 8. So, and 16 is 2 to the power of 4. So let me go ahead in steps. So we have this here. Outside we have half. That is square root. 16, I could write this as 2 to the power of 4. 16, correct? 2 times 2 times 2 times 2. And now I will write this as, I replace 2 by, 8. I have to write 8, right? So 1 over 3. So 8 equals to 2 to the power of, 2 is equals to, right? I could write this as 8 to the power of 1 over 3 as 2, right? So let me write this as, let me change the ink now. 8 to the power of 1 over 3 is 2. Cube root of 8 is 2, right? So instead of 2, I will write cube root of 8. You get an idea. This is what I'm going to use now. So instead of 2, I'm writing cube root of 8. Does it make sense to you? And rest I'll maintain as it was. So 4, so I'll write 4 over 2. I just multiply these two. Is it okay? So what we get here is log to the base 8, and we got the same base. That was critical. 4 divided by 2 is 2, so we get 8 to the power of 2 over 3, and that gives us the answer as 2 over 3. So log to the base 8 of square root 16 is 2 over 3. So it's kind of tricky as you move forward. Now let's do a few more examples, and this time we are getting back to writing logarithmic functions as exponential forms. This is very simple, but it helps you to understand how to solve logarithmic equations which are about to come now. So if you have log to the base 2 of 1024, we know the answer is 10. If I have to write it in exponential form, I can write like this. Retain the value of x, which is 1024, equals to base is 2. So base is 2 to the power of exponent 10. Do you see that? So that becomes your exponential function. So here we'll write 3 to the power of minus 4 on the right side and 1 over 81 on the left side. We are done. Here we'll retain 8, whatever the x value is, and half to the power of minus 3 gives you the exponential form of the given logarithmic equation. It is as simple as that. So 1 equals to 5 to the power of 0, and in this case 27 equals to 3 to the power of 3, and in this case log to the base 10 is 10. Is that okay? So I didn't really write this. It is equals to 1, so I could write this as 10 equals to 10 to the power of 1. Correct? So that is how we could write this particular expression. So let's move forward and solve exponential equations. Now here the exponential equation is 9 to the power of 3x equals to 27 to the power of x minus 3, and we have another one which is 4 to the power of 5x minus 1 equals to 8 to the power of 8x plus 7. I'd like you to pause the video, answer these questions yourself, and then look into my suggestions. I hope you are enjoying the journey so far, and in no time we are going to complete the review on logarithmic functions. Thanks for your patience. Strategy is to have the same base. Now to make same base, we can write 9 as 3 square, and we can write 27 as 3 cubed, correct? And then we can equate the exponents and solve the equation. So I'll replace left hand side 9 to the power of 3x as 3 squared to the power of 3x, and on the right side 27 as 3 cubed to the power of x minus 3. By doing so, we have made their bases as same. So now we can write left side as 3 to the power of 3 times 2, 6x, and on the right side we get 3 to the power of 3 times x times 3 times minus 3, which is minus 9, correct? Since the bases are same, exponents should also be same for the equation to be valid. And therefore, 6x is equals to 3x minus 9. And now we can solve for x. So we get 6x minus 3x equals to minus 9. 3x equals to minus 9. And x is equals to minus 9 by 3, which is minus 3. So the solution for the first equation is x equals to minus 3, correct? You can actually follow the same strategy and solve the next exponential equation. Now in this equation, we are given 4 to the power of 5x minus 1 equals to 8 to the power of 8x plus 7. Now I can write 4 as 2 squared, and I can write 8 as 2 cubed. So by doing so, we'll have the same base for both the sides. So let me rewrite 4 as 2 squared, and then to the power of 5x minus 1 equals to 8 is 2 cubed, then to the power of 8x plus 7, correct? Now with the same base 2, let me multiply 5x minus 1 by 2, I get 10x minus 2. On the right side, we'll multiply by 3, getting 24x plus 7 times 3, 21. Since the bases are same, we can, this is 10x, we can equate the exponents and calculate the value of x. So we have 10x minus 2 equals to 24x plus 21. Bringing x's together, we can write this as 10x minus 24x equals to 21 plus 2. That gives us minus 14x as equal to 23, or x is equals to minus 23 over 14 as our answer. So x is minus 23 over 14 for the next example. So with that, I think we have solved these equations. Let's move on to the next set of equations. Here we have to solve exponential equations. Leave answer in exact form. You'll notice that the bases are different, right? 5 and 3, 9 and 4, and we cannot make them same. Now in such situations, we have to take help of logarithms to solve. Let us see how to solve such equations. So we'll take log on both sides. So for the first one, if I take log on both sides, I get log of 5 to the power of x minus 2 equals to log of 3 to the power of x plus 5. Applying the rules, we get x minus 2 times, let me put it in bracket, log of 5 equals to x plus 5 times log of 3. So let's open the bracket and then club the x terms. So we have x log 5 minus 2 times log 5 equals to x log 3 plus 5 times log 3. Bringing x terms together, we have x log 5 minus x log 3 equals to 5 log 3 plus 2 log 5, right? So these are to the base 10. Taking x common, we get log of 5 minus log of 3 equals to 5 log 3 plus 2 log 5, correct? And then we can say what x is. So x is equal to 5 log 3 plus 2 log 5 divided by all this, which is log 5 minus log 3. So that is the exact solution. If this was right to decimal numbers, we'll need to calculate it using calculator and write down the result. Perfect. Let's do the second part now. Method is going to be exactly same as we did for the first one. You can actually pause the video, do it yourself, and then look into my suggestions. So we'll take log both sides. We get log of 9 to the power of x minus 4 equals to log of 4 to the power of x plus 2. So that gives you x minus 4 times log 9 equals to x plus 2 times log of 4, and that is x log 9 minus 4 log 9 equals to x log 4 plus 2 log 4, right? Or x log 9, bringing this here, x log 4 equals to 2 log 4 plus 4 log 9. Taking x common, we get log of 9 minus log of 4 equals to 2 log 4 plus 4 log 9, or x is equals to 2 log 4 plus 4 log 9 divided by log of 9 minus log of 4, correct? So that is how we can solve such equation. So let's move on and solve other questions related to logarithms. Now let us try to write given logarithms as single logarithm. We have two examples to work with. You can always copy these questions, solve them, and then look into my suggestions. So we'll apply the rules of logarithms. So when we have negative, they get divided. When they have positive, they get multiplied. And this acts as the power, right? So we'll kind of review all the rules with the help of these two examples. So first step, we have log of something minus log of something else. Since we have the same base, which is 10, we can combine them and write as x squared plus 2x minus 3 divided by 2x plus 6, right? So if that is a rule, so log of a minus log of b, same base, it is log of a over b. Now to simplify, it's a good idea to factor. The numerator, we are looking for product of minus 3, sum of 2. So that could be 3 times minus 1, right? So we could write this as x plus 3 times x minus 1 divided by 2 common, we get x plus 3 here. Now that could be combined. X plus 3 can cancel out. So you could simplify this as x minus 1 over 2. So that is how you can write this as a single log, right? That's the meaning. Now whenever you have expressions like this, you should also write down all the restrictions which are based on the given situation, right? So we know log of something should always be greater than 0. So I'd like you to work on the restrictions. When we are talking about this parabola in the numerator, let me just sketch and show you here. That parabola will look like it'll have two zeros, one at minus 3, one at 1. So it may be something like this, right? So opening upwards. So here, this particular function, this is for that, is actually negative between minus 3 and 1, right? So this is minus 3, this is 1. The other function here, which is 2x plus 6. Now this function, 2x plus 6, is a straight line, right? Which factored as 2 times x plus 3, right? So that means it has 0 at minus 3. So here it has 0. And then from here, it is positive slope. So it's kind of going up. Do you see that? Now if you see these two functions, what we realize is that both of these functions are positive only after 1. Do you see that? Otherwise, one of them is negative, right? This is negative here, and on the other side this function is negative. Therefore, this particular logarithms which we are talking about has a restriction, and here the domain is x should be greater than 1, right? So x should be greater than 1, so that is the domain, or you can say restriction on this logarithmic function. Perfect. So whenever we write a single log, it is a good practice to also write the domain. So we can say here x is greater than 1. So I've also considered what cancelled out. Do you see that? Anyway, so that is very important to understand. Now let's do the second question here, which is 3 log a. So 3 log a, using the power rule, we could write this as log a cube, right? And here we could write this as log y to the power of 4 minus log z square, correct? So that is how you could write this logarithms. Now applying the property, we get log of, we have to multiply these two, which is a cube times y to the power of 4 divided by z square, correct? So that becomes the expression in the given scenario. So that is how you have to work on these functions, correct? And of course, the value of a, y, and z all should be greater than 0, right? So in this case, a, y, and z should all be greater than 0, right? So that becomes the restriction. So I hope it is very clear how to write expressions as single logs, right? Now let's go to the next example. We have two logarithmic equations, and we will see how to solve these equations. So let's begin with the one on the left side, which is log to the base 2 of 3x minus 12 is 6. So we could convert it into exponential form and write this as 3x minus 12 is equals to 2 to the power of 6, correct? So that is the way we should begin. And now we have a linear equation, right? What is 2 to the power of 6? Let's see that. 2 to the power of 6 is 64. So we replace that by 64. So we have 3x minus 12 equals to 64. Taking the terms together, we have 3x equals to 64 plus 12. So 3x is equal to, add it, 76. And x is equals to 76 over 3. And that is 76 divided by 3 gives us, in decimals, 25.3 reckoning. So that is good enough, right? So this is good enough. So our answer in this case is x is equals to 76 over 3, right? Now, we should also check that it falls in the domain. So the domain is that 3x should be actually greater than 12, or x should be greater than 4. Perfect. And this is definitely greater than 4, so it works. Let's solve the next equation now, which is log of 9 x minus 5 plus log base 9 x plus 3 equals to 1. So you could rewrite this as log to the base 9, and that becomes the product, which is x minus 5 times x plus 3 equals to 1. Now we'll convert it to the exponential form, writing it as x minus 5 times x plus 3 equals to 9 to the power of 1, which is 9. Let's open the bracket and then simplify. So that gives us x squared plus 3x minus 5x minus 15, bringing 9 to this side, minus 9 equals to 0. That is x squared minus 2x, and that is minus 24 equals to 0. So we are looking for product of two numbers to be 24 minus, and their sum as minus 2. 6 and 4 can work for us. So we can write this as 6 x minus 6 times x plus 4 equals 24. It gives us two solutions. One is x equals to 6. The other one is x equals to minus 4. Now, we have to look for extraneous roots, right? So we have to always check for extraneous root. All solutions may not be true solutions. Now, what you notice here is that x has to be greater than 5, and in this case, x has to be greater than -3. So this prevails, correct? So we have a restriction. X has to be greater than 5, so this is extraneous root, not valid. So the only answer here is x equals to 6. So our answer is x equals to 6, right? So with that, we have seen what logarithmic functions are, how are they related with exponential functions, how do we write logarithmic functions as exponential functions, and we have solved equations solving logarithmic and exponential functions. I hope that helps you to understand and review the whole concepts. Feel free to write your comments and views, and if you like and share my videos, that would be great. Thanks and all the best.